The length of a rectangle is increasing at a rate of 2 feet per second. That's a quickly expanding rectangle. And its width is increasing by 3 feet per second. At what rate? It sounds like a horror movie. Like where the blob is expanding. Okay, focus. At what rate, what rate is the area of the rectangle increasing when the length is 6 feet and the width is 7 feet? Okay. So they say, what is the rate? At what rate is the area of the rectangle increasing? So first thing we need to know is a formula for the area. So area equals length times width, and then we want to know the rate of change of the area with respect to time. So we'll do d area dt. And so we'll take the derivative of the left side, derivative of the right side. And this is the product rule. UV equals UV prime plus U prime V. Change colors, add excitement. So we'll have L dW dt plus dL dt times W, where L is length, W is width. Then I'm just going to plug in some variables. Plug in the variables. I can't go back to green. Blue. Okay, so this says the length is increasing at a rate of 2 feet per second. So 2. And its width is increasing at a rate of 3 feet per second. 3. What is the area when the length is 6? 6 times plus 7 times. I guess the 7 should be on the other side. Doesn't matter. So length, width increasing rate per second, and length increasing rate. Okay, we got this. So this is 18 plus 14. Math. I think it's 42. Is it 42? So we'll do 18 plus 2 plus 12 equals 20 plus 12 equals 32. I said 42, didn't I? 32. Luckily 42 is not a possible answer. So 32 will be the answer. Check the units real quick. So we have area per unit time. So it would be feet squared per second. Yep, that seems reasonable. And that's how you do this one. So you're like, all right, need to find change in rate of area with respect to time. So you need an equation for area. Then you take the derivative of that, and it gives you area per unit time. But since you have two variables, you have L, which is changing with respect to time, and width, which is changing with respect to time. Then you have to do the product rule. As a quick sidebar, you might think, wait a sec, what's this with respect to t sort of thing? It's like, well, okay. Does the product rule work with constants? So let's do this a little bit differently. Let's say that area equals length times width, but W equals 3, always, no matter what. And so you're like, well, let's do the product rule here. Equals L dW dt plus W dL dt. The product rule. And what happens then is, since W always equals 3, dW dt equals 0. And so this whole side goes to 0. And this is what you're familiar with when you have a constant multiplied by a variable. And then you're trying to take the derivative with a constant out in front of it. So I have derivative with respect to x of 3x squared. You have this constant out here. And that's how the constant works. So then this would be 3 times 2 times x, which equals 6x. So that's why the product rule is consistent with life. It makes sense. So you can use the product rule with constants even if you wanted to. It's just that one side of the equation's going to cancel out. All right, sidebar ended. And that is how you solve a rate of area change for a rectangle.